All right, so we're going to look at one of the most stereotypical type of situation you'll be dealing with in a dynamics problems. And this is known as the Atwood Machine. So what an Atwood Machine is effectively just some sort of pulley that causes the direction of acceleration to change in a system. Not the magnitude, just the direction of it. All right, so you have some sort of pulley going on. These problems are actually, I think, kind of fun to solve. But then again, right, I am a physics teacher, so. Anyway, you can find this problem in your textbook. It's problem number 7 on page 176. But anyway, so we have a Benedictine abbot at Westminster Abbey, which was training a novice to ring the bell. Practicing without speaking, they grasped ends of a rope dangling over a pulley from a machine left by Reverend George Atwood. On occasion, the abbot stepped off a platform, grabbing his end of the rope 2.5 meters off the floor. All right, so the first part here asks us to construct a free body diagram for the abbot and the novice. So just looking at this prompt, we're not really told what we're solving for and what the end goal is. I think we're going to be told kind of step by step what to do. Before drawing out the free body diagrams, let me scroll up a little bit. I do want to just sketch out what kind of visually is going on here. All right. What we have is basically some sort of pulley, so I'll just represent that with a circle. And this pulley is actually going to be massless, frictionless. A lot of times you'll see that word actually, that phrase mentioned in a problem, which is meaning later on this year we're going to be dealing with pulleys that have mass, but nonetheless, we've got some sort of string or rope hanging from each end of this pulley straight down, where we have then one of each of these people on either end of this rope, right? So basically here is one person pulls down and the other person moves up and vice versa. So here we're told, let's assume here on the left is the abbot, right? Is that the word we're using? Yeah, abbot. Kind of a weird prompt, but anyway. Abbot, and then the novice, we'll say here on the right. So we're told that the abbot steps off a platform, grabbing his under the rope that's 2.5 meters off the floor. So the abbot's going to fall down, which means that the novice is going to be pulled up. So we have basically kind of motion this way. So when our pulley here rotates, it's going to rotate counterclockwise. All right. So let's go back to looking at the free body diagrams here. Let me actually keep our depiction here. So first, let's look at the abbot. So we'll draw a dot representing our abbot. We've got two forces going on here. All right, we always have the force of gravity acting on our object, so on our abbot, and then we also have tension. Tension acts in the direction of the rope, so that's going to be straight up. I'll label that with the T for tension. And then we have the force of gravity. So since this abbot steps off, and so initially our rope here is not moving, and then it starts to move, our acceleration is actually going to be downward. Right? Something goes from not moving to moving, the acceleration's in the direction of whatever the motion is. So then I know my free body diagram here, the force of gravity must be longer than the tension. Let me actually draw tension a little bit longer. Anyway, so this is force of gravity, and I'll put a little a here for the abbot. And then for the novice, we have the same named forces, right? So here's a dot representing our novice. We have tension. Now, when we're dealing with this tension in the rope, since it's the same rope and it's over a massless, frictionless pulley, this rope has the same tension. So we have the rope is upward, acting upward on our object, and it has the same magnitude as the tension acting on the abbot. Now our novice is going to be accelerated upward, so its force of gravity has to be smaller than tension. All right, so there are our free body diagrams. Okay. So, part 2 of this problem. Apply Newton's second law to express the acceleration of the system in terms of the weights of the Abbot and the Novice and the fundamental constants. Alright, so we're told here to write things in terms of weight, not mass. So we're allowed to leave it in terms of the force of gravity. Alright, and any fundamental constants. So what fundamental constants mean is the acceleration due to gravity, so lowercase g. And that's basically the only fundamental constant we've actually dealt with. So, later on actually we'll be dealing with a capital G. That's all I can think of right now. So, applying Newton's second law. So that's net force is mass times acceleration. So going back to our previous picture, we want to set up a coordinate system. I'm actually going to have a different coordinate system for each Abbot, or each person here. So I'm going to say taking a step back here. A good problem-solving approach with particular Atwood machine problems is calling the positive direction of acceleration. So for my Novice, my acceleration is upward, so I'm going to call upward my positive y direction. The Abbot is accelerating downward, so I'm going to call downward my positive y direction. The reason for this is then my acceleration is going to be the same kind of direction for both, since as the Novice accelerates up, the Abbot accelerates down. So the acceleration of both objects, since they're connected with a rope, is going to be the same magnitude, and now we're not going to get confused with negative signs. It's kind of the long and short of it. Alright, so let's first look at the Abbot. So summing the forces on the Abbot, we have our net force, which is mass times acceleration, so mass of the Abbot times acceleration, is equal to, I have a positive gravitational force and a negative tension. So force of gravity of the Abbot minus tension. For my Novice, alright, my net force is mass times acceleration. Again, their accelerations have the same magnitude, so I'm going to express them just both as A. And that's going to be equal to, now this time my tension's positive, and I have a negative force of gravity of the Novice. Alright, so basically I've set up my system of equations here. I just need now to make sure that the terms are in terms of weight of the Abbot and Novice and any fundamental constants. So since we're trying to find acceleration here, what I'm not allowed to have in my expression then is tension. Right? We're allowed to have force of gravity, and I don't want tension. And actually, we're not allowed to have mass either, so we'll have to deal with that in a minute. So since I do not, basically all I need to do now is rearrange one of these equations for tension and plug it into the other expression. So that'll get us one equation with no longer any tension involved. So looking at this expression here, this will give us, for tension, this is going to be mass of the Novice times acceleration plus the weight of the Novice is equal to tension. Alright, so kind of plugging that into the first equation, we have mass of the Abbot times acceleration is equal to the force of gravity of the Abbot minus tension, which is the whole expression I've just found. So mass of the Novice times acceleration plus force of gravity of the Novice. Alright, so bringing acceleration to the same side, we have mass of the Abbot times acceleration plus mass of the Novice times acceleration is equal to the weight of the Abbot minus the weight of the Novice. And isolating acceleration, well actually let's take a moment here. Let's isolate acceleration. All right, so we factor out acceleration from both sides here, and we have mass of the Abbot plus mass of the Novice is equal to force gravity of the Abbot minus force gravity of the Novice. So let's do a little math trick here before I do kind of the next step. So since in my problem I want our answer to be in terms of the weight and not the mass, I have the problem right now where on my left hand side I have values for mass. Well, weight is just mass times the acceleration due to gravity. Right, so what I'm going to do here is multiply both sides by the acceleration due to gravity. There's no problem with doing that as long as I do it to both sides, because I'm just multiplying by the same factor. So the left and right hand side are still going to be equal. So I have acceleration times mass of the Abbot times acceleration due to gravity plus mass of the Novice times acceleration due to gravity is equal to force gravity of the Abbot minus force gravity of the Novice, that whole thing times the acceleration due to gravity. And that's convenient because this term and this term can now be simplified, as this is the weight of the Abbot and this is the weight of the Novice. So then our last mathematical step then is just to divide the two, and I'm running out of room, so I'm going to write it here to the left. But divide both sides by my expression here in parentheses. So in the end, my acceleration is going to be, let's see, the weight of the Abbot minus the weight of the Novice times acceleration due to gravity divided by weight of the Abbot plus the weight of the Novice. And there's my expression. All right, so this was kind of a very kind of AP step here in solving this problem, because it prompted you to solve and have your final answer in a certain way. Right, so first it says apply Newton's second law, so that's what we did with summing the forces and writing it in terms of mass times acceleration. But we couldn't just leave it at that, because the prompt here specified that we have to write it in terms of weight and any fundamental constants. All right, so we had to make sure our final answer, when looking at it here, is solved for acceleration, right? And it's in terms of weight and fundamental constants, which is g. That's allowed. All right. So we had to do that little mathematical trick to do that. All right. I'm going to do a little pause here, and you can continue this problem in the next video.